Okay, welcome everyone. My name is Philipp and I'm going to be talking about immutability in Scala, and in particular, how immutability is used in popular open source projects. And I'll try to quantify and also explain to some extent the use of immutability. And this is, I should say, joint work with Ludwig Axelsson, who worked on this as part of his master's thesis. And, well, again, you should use the Scala Days app, obviously. Right, so the first question is, like, why would we care about immutability in Scala? And, well, it's pretty clear that Scala is a powerful functional language. As Martin told us yesterday, the principles of Scala are around types, functions, and objects. So functions are one of the cornerstones of Scala, and of course many people use Scala as a flexible and powerful functional language. And now functional programming, of course, emphasizes programming with first-class functions, that is for sure, and also typically programming with immutable data structures. Now, I'm not trying to give you a definition of functional programming, because there's many people who've burnt themselves trying to do that. In particular, there's prominent functional languages like Lisp and others, and ML, which have imperative features. So certainly I'm not talking about pure functional programming here. But nonetheless, immutable data structures are quite important, and not only that, but also for reasoning about our programs, and I'm going to give you some examples. Now, concurrency safety is, of course, very important, and I've spent many years working on concurrency libraries and programming models and whatnot, and certainly immutability significantly simplifies writing concurrent code. And later on, when I show you some numbers about immutability usage in Akka, we'll see that also the Akka team actually embraces immutability a lot. Now, so who of you has used Apache Spark or Flink before? Okay, so like 40% maybe, 30–40%. Well, the issue here is that in such a distributed framework, fault tolerance essentially relies on immutability. Because, for example, in Spark, there's a notion of lineage where the data of a crashed machine is reconstructed based on, some data on stable storage plus a lineage that describes how to transform the data to arrive at the state of the current state of the data, or the current collection that we're working with. And for this only works if the data in your RDD, say in Spark, is immutable. Right, so it's actually crucially important, immutability, to have actually fault tolerance in these systems. And yeah, so there's numerous applications, of course. And also, if you look at Java, I picked the Java doc here because unfortunately the Scala doc for maps is not as detailed. But here we see that in the map interface in JDK 8, it says that great care must be exercised if mutable objects are used as map keys, right? And moreover, it says that actually the behavior, and trust me on this, the behavior is undefined if the object is changed in a manner that affects equals comparisons, while the object is a key in the map, right? So, and of course, the same issue we have in Scala as well, and maybe there should be a note in the Scala doc as well about this, because obviously, if you insert an object into a map, you compute the hash code, and if you later on mutate the object, that will change equality potentially, right? It may affect equality, and then you may not actually be able to find what you're looking up in the map afterwards. Okay, so clearly there's numerous bugs, I assume, resulting from these things. And I want to give you one more rather concrete example about touching on referential transparency. What's referential transparency? In fact, you can look at an expression and say whether it's referentially transparent or not. And it's referentially transparent if we can replace the expression with the value that it evaluates to without changing the program's behavior. Now, we can, based on this, on referentially transparent expressions, we can talk about referentially transparent functions, where we say that a function is referentially transparent if, when we apply the function to the same value, we get the same result. Right? Because if you have the same, if you look at a function application or two function applications with the same argument value, then the application is an expression that's only referentially transparent if the function has an according property that we call referentially transparency as well. Right, and so to make this more concrete, let me give you a very simple read-only function, right? It only reads values. So in this case, we have two simple class types as arguments, as parameters, and we just compute the sum of two integer values. And also the assumption is that this member, that age, is just a getter that returns an integer. And in fact, it's, right, so we assume that age does not mutate its receiver. So that means p1.age will not mutate p1. That's our assumption. So it's a read-only getter. And obviously, sum of ages, the function, also does not do any mutation itself. Now we can ask, well, is this function referentially transparent? So who thinks the function is referentially transparent? Okay, a very small, rather small percentage. Maybe some of you are not sure. But there are certainly several people who think it's referentially transparent. Let's have a look at an example. So let me give you a class definition. Of course, I'm unfair because I haven't shown this to you before, but let's say we have this class person, which has a name and an age is a var, which means that we'll have both a getter and a setter for age. And we can create two persons, John and Judy, and compute the sum of their ages, and that results in sum 1. And now it happens that John has his birthday, so his age increases, and now if we apply sum of ages to the identical arguments, sum 2 is not the same as sum 1, right? And note here that I've not just passed a value, an argument that is equal to what I've passed before, but I've actually passed identical objects, right? So they're even syntactically identical. And still the result is not the same. Now this is kind of strange, right? Because the function sum of ages, it really does not, only reads. It's a read-only function. Now how come it's not, how come referential transparency is violated here, right? It clearly is violated because if, we get with the same arguments, we get two different outcomes. Now the reason is that sum of ages is actually, it's not a pure function. If you look at it again, it may be read-only, which it is, but it's not free from side effects. And the reason is that it is actually reading a mutable state, right? It is actually reading from a stateful object, and that's an effect, right? And now, first of all, I'm sure there's people who are not aware that this would have to be considered to be an effect. And second of all, it's very hard to see that we're in fact breaking referential transparency here, right? Because we don't know, the type system, for example, doesn't tell us about age. I mean, we can, of course, go and look at the implementation where we see that there's not just a getter, but there's actually it'll actually read mutable state. But that requires us to look at the definition of class person, right? So even with simple functions like this, it's hard to see what's happening, and unfortunately, the type system doesn't help us there, right? So now clearly, there's many people who use immutability in Scala, and I'll show you numbers later which show exactly that. And in fact, there's many ways in which many features and constructs that we can use to introduce immutability or to make our type definitions immutable. For example, we have predefined value types. These are immutable, and that's good because these are the some of the basic building blocks we have. We can also use val members in our templates, right, in our class definitions and so forth. We can also use lazy vals, and that's really nice because a lazy val does not destroy the property of immutability unless we do something very strange for the initialization of a lazy val, right? But typically, the lazy val is a perfectly fine way to have as a member of an immutable type. Also, if we just create simple case classes, then these are actually immutable by default, right? Because if we don't declare or inherit any var members, and all our field types are immutable, well, it means that our case class is immutable. Yeah? And of course, I think there are many usages of these case classes, and again, we'll see some numbers later again. We also have value classes in Scala, right? And a value class is very interesting because it has just one val member, and it can only mix in so-called universal traits. So who of you knows what a universal trait is? Okay, so we have 2% of the audience of Scala Days, which is already a selective crowd, so let me tell you a little bit about that. But some examples here. So, of course, an immutable case class, here's a very simple example. It's just a case class with some fields that have immutable type, string and age, right? So that's clearly immutable. Now about the value class, we can define, again, an immutable value class very easily. So for example, class meter, right, wraps a double. So that's its sole val member. And of course, we extend any val to point out this is a value class, or to make it a value class. But we also mix in this printable trait. And printable is very well behaved because it only introduces methods. Like it does not have its own val or var members, right? And in fact, the type checker enforces that for traits that extend any, right? So that's how we introduce so-called universal traits, right? So a universal trait extends from any, and it does not declare any vars or vals. Yeah, so it really just only has methods, and so it's fine to mix those traits into value classes, right? Of course, it can change the allocation behavior of a value class, right? And this is well documented in the Scala documentation, right? But in this case, we're not actually interested in the allocation behavior, right? We're only interested in the immutability property. And we can say that a value class is immutable if the type of its sole val member is also an immutable type. So this is a nice way to, again, introduce an immutable type. Now, let's say we would like to introduce a constraint on our types that they should be immutable, right? Like we could try something like this. Let's say we have a method, send message, which is supposed to send an object from one concurrent process to another, for example, between two actors, right? And of course, this is hypothetical. That's why I called the method differently from those in Akka, right? Let's say, but clearly it may be useful to have such a method in the absence of a more powerful system like La Casa, which I talked about at Scala World. But this method basically says, well, we have, first of all, it's a generic method with a type parameter, but we have this context bound, right? So t::immutable. Context bounds, of course, are used for type classes, and in this case, we introduce this immutable type class. And so this could be a constraint that says, well, you can only send messages of types that are immutable, right? And so this expands to an implicit parameter. And so now we need evidence that some type is immutable, right? Now, there are some issues with that, right? Like first, the implicit values, the implicit evidence that we have to introduce must be introduced manually, right? Like the compiler does not come up with the evidence itself. We have to manually introduce them, and that's some boilerplate, but also maybe what's more tricky is that we have to also trust these manual definitions. We could introduce nonsensical definitions, right? So for example, we could have a wrong implicit value that says that a mutable set is immutable, right? So we could introduce this and circumvent the previous constraint. Now, of course, this may be useful as an escape hatch, but it's certainly not so nice that everything is manual, right? The introduction, the checking as well, the checking whether a type is actually immutable, that's manual as well. So, right. So in this sense, programming with immutability is a bit limited in Scala right now, right? Of course, we have good ways, like I mentioned, to constructively create types that are immutable. But we cannot express immutability as a requirement of our types. And moreover, we actually don't really know how immutability is used in Scala, right? It's more like folklore. I mean, sure, we try to make our things immutable, perhaps, right? Use some intelligent caching, we use lazy vals, etc., right? But no one actually knows. If you look at some of the largest, most widely used open source projects, how do they actually make use of that? Are all the case classes immutable or not? Or, what's going on? So this is what we try to do, is to look a little bit at existing projects. And I think this is interesting because, a language also gives you certain defaults, right, for things. Could be modifiers and other things, right? And based on these statistics, actually, I think this is maybe food for thought about what are good defaults in a sense, right? So in the remainder of the talk, I'm gonna show you some empirical results where we try to evaluate in open source code bases, how much of their type definitions are immutable, and also we looked at causes for mutability, or causes for, I'm going to go into more details later, but basically what makes it so that certain classes cannot be detected as immutable by our analysis, essentially. Right, so first of all, there's many different notions of immutability that you could look at. In fact, in the scientific literature, there's a very wide range of immutability notions. And in this talk, and for our results, I only look at the immutability of types or type definitions, because there's actually a somewhat more refined notion where we look at reference immutability. And reference immutability basically says, well, if I have a reference to an object, does this reference enable me to mutate the object? If it does not, then it's an immutable reference, right? But there may be other references that do allow mutation. Yeah, there could be aliases, other references, which do allow mutation, but for particular references, we could find out whether that reference allows us to, or we could enforce that for a given reference, it does not allow mutation. So, for example, it does not allow calling a method that is mutating, right? It does not allow calling impure methods, for example, right? But that's rather involved. Typically involves complex type systems. Yeah. So the immutability properties that we looked at, we'll look at 3 different ones, and these are actually fairly simple. They're actually so simple that when we started this project, I didn't actually think that they would be that useful. Turns out they're very useful because there's lots of code which has these properties, right? And so the first property is very radical, where we say let's say a class definition is deeply immutable if it does not declare or inherit a var member, and all its fields refer to deeply immutable types themselves, right? So it has only each instance of the class has only references to deeply immutable objects. So transitively, this completely immutable object graphs, essentially, right? And of course, that's the strongest form of immutability we could have. And in fact, the ways to initialize such a deeply immutable object are very limited. And if you use a very simple notion like we did, you can only construct an object by calling the constructor, say, right? And that's your only chance to initialize the object. Turns out many classes in practice, in fact, have this property. Of course, there are other classes that do not have this really deep immutability property. And that's what we call shallow immutability, where, again, the class or trait has only val members, so there are no declared or inherited var members. But, a val member could refer to an object, or could have a type that's not deeply immutable. Yeah. So that's, of course, kind of a shallow notion here. And the third property, that's very important, especially for Scala, which is the case where the deep immutability depends on the instantiation of type parameters or type members, right? So, for example, let's say I have a collection type, list of t, right? Then list itself may be immutable because it sort of doesn't itself introduce mutability. Of course, there are different implementations, like in the Scala core library, where there is mutability under the hood, but it's not observable, right? But if I instantiate the type parameter with a mutable type, then clearly I don't have transitive deep immutability. Yeah? So list of t, an instance of list of t would only be deeply immutable if t is instantiated with a deeply immutable type. And so that's what we call conditional deeply immutable, which means that if all type parameters and type members, fortunately in Dotty they are the same, if these are all instantiated with deeply immutable types, then the type definition we're looking at is also deeply immutable. Right, and so the questions we're interested in are 2. The first question is, well, how frequent is each of these properties? And like I said before, I didn't think that deep immutability, like we defined it in this very simple way, would be that common. Yeah? But it's interesting to see how frequent these properties are. And we also looked at, of course, classes, traits, and objects separately, but we also distinguished between different kinds of classes. So we distinguished between case classes and also anonymous classes, objects and case objects, and so on. And turns out there's significant differences in how these different template definitions are constructed with respect to immutability. Right, and so the second question is, if we have a, say, class or trait definition that's not deeply immutable, what are the most common reasons for why they do not satisfy a stronger immutability property? Right, so for example, let's say I have a mutable class declaration. Why is it mutable and not shallow immutable, let's say, right? Or let's say I have a shallow immutable trait definition. Why is it only shallow immutable and not deeply immutable, right? So it's interesting to see, like, where does it break, basically? Yeah. Because these are points where our immutability analysis would have to be refined so that we can potentially detect more type definitions to be immutable that actually are immutable, right? Because certain things like internal caching, they may look mutable, right? Because we use var members, let's say, but in fact, the state is not observable, right? They're actually stateless, right? Even though they have a var member. But right now, our analysis clearly cannot detect these cases based on our simple notions of immutability. Right, and so to answer these questions, we implemented a compiler plugin for Scala 2.11, which may look like an ancient version by now. One of the reasons why we looked at 2.11 first here was to be able to analyze as many open source projects as possible, basically, and also because of the time frame when we started this project. So, of course, another factor. And basically, the way our analysis works, roughly, is to say, well, for each template, and by the way, template, we use the word as it's used in the Scala specification, right? So if you have a class declaration, then everything that starts with your superclass and the traits that you're mixing in, that's called the template, right? It contains all the definitions in the class declaration. And so for each of these templates, we maintain a immutability value from a lattice, and the lattice just says like which property is true at the current point in the analysis. And so we start with bottom, which means we don't know anything about the immutability, essentially. When we start analyzing a template, we start with the assumption that it's deeply immutable. And so the idea is that as we analyze the template and also its parents and mixed-in traits, we discover more evidence that says, well, maybe it's not deeply immutable, but shallow immutable. So then we go up in the lattice, we do a monotonic update, where we say it's no longer deep, but it's now shallow immutable, according to our evidence, right? And of course, the sort of the top value is mutable, where we discovered something that makes it mutable, and that's the final value. There's nothing that will improve this value, essentially. And we use this programming model called reactive async, which I talked about actually last year at Scala Days in Berlin, which gives you these lattice-based variables. And what's nice about it is that you can, on the one hand, you can do these monotonic updates, but you can also resolve cyclic dependencies. And the resolution of cyclic dependencies is crucial if you look at class definitions, for example, right? Like that's what all compilers have to crucially work with, right? Is cyclic dependencies, and our framework allows us to work with that, where we have values of lattice variables depending on the values of other lattice-based variables, and there could be cycles in their dependencies. Yeah, so if you're interested in more details, have a look at my talk. And this immutability analysis is also implemented here. So the current, most current version you find on GitHub here. And you can pretty easily just analyze your own projects with that. And currently it's easy to use for SPT and Maven, so yeah. Right, so let's have a look at the actual projects that we analyzed, right? So we tried to look at some large pieces of code. For this first iteration, basically, we needed to analyze projects that do not have many external dependencies, because it's simply that our framework is not so flexible yet to conveniently allow you to do that. So we focused on projects like the core library and also the Akka actor package, which has minimal dependencies. Yeah, but we also looked at other projects like Scala test that yeah, are very large. So at some point, Bill Venners has to tell me why Scala test is so large. Yeah. Good. We also, so besides these projects, we also have results for Scala.js, which are kind of interesting, Scala FMT and so on. And of course, this would be cool to kind of gradually expand to more projects. And without further ado, let's have a look at some results, right? So first question, how frequent is each of these three immutability properties for the different kinds of template or different kinds of class or trait or object definitions? And if you look at the Scala core library, so by the way, don't be afraid about all these numbers. I will tell you that they're actually very simple to read, and I think they're more interesting than pie charts. I'll show you pie charts later, but I find these numbers are actually very interesting. I'll point you to the most important numbers you should look at. And by the way, sorry about the commas in there. That's a European glitch here. Should have been periods. So first of all, what can we see here? I have some circles. Right. Well, first of all, I should point out that we have these different kinds of templates. As I mentioned, we distinguish between case classes and classes that are not case classes, because they will have very different results. Anonymous classes are also separate, because they, for example, they have type parameters already instantiated and so on. Traits are also separate. Objects and case objects, again, are separate. And the numbers are very different for these different kinds of templates. Overall, we can see that there's less than half of all templates are mutable. That's encouraging. Also, we can see that the numbers for classes and non-case classes and case classes are very different. So where we have about 50% of all class declarations that are mutable, we only have 25% of all case class declarations that are mutable, right? That's a big difference. What's also interesting is that with this very naive and simple and very restrictive notion of immutability, which is deep immutability, we have about a third of all of these templates directly satisfies this property. And that's something that I was completely surprised with, right? So this is extremely strong notion of immutability, right, is sort of satisfied out of the box. Shallow immutability is also important, not very high. We have other projects where it's much higher. We also have conditionally deeply immutable, which is quite significant here, like 15%, right, where basically if the type parameters or type members are deeply mutable, then the template itself would be deeply mutable. And also you'll see that there's a certain cells here where we have zeros, and this is expected because there is, of course, no way for an object to have a type parameter, and neither for an anonymous class. So, of course, these numbers will always be 0. And fortunately, our analysis found that out as well. So, good. Anything else interesting here? Let's see. I have more interesting things to say about the next project, I think. Also, we want to compare them. That's where it's kind of interesting. So if you look at Akka actor, that's very astonishing, where it has less than 20% of declarations that are mutable, according to our analysis. And so compare that with 47%, right? And not only that, but if you look at deep immutability, like just this extremely strong notion of immutability, we have more than half of all the declarations that satisfy that property. So Akka team, well done, right? Very solid engineering here. There's very little I can break in this. So and the other thing is, like, there's repeated patterns. So if you look at sorry, I first wanted to tell you about these percentages again. So like, if you compare case classes with non-case classes, again, like, there's a big difference here in numbers of mutable templates, and of course the reverse trend is here. So like, there's 43% of all case classes are deeply mutable, whereas it's only 27% for non-case classes. And the other thing that's really interesting is that singleton objects, whether they're objects or case objects, there's a very low percentage of those that are mutable. In fact, we'll have other projects that have an even lower percentage, right? And so, like, the fact that we assume by default that there can be mutable, I think is yeah. I would love if they would be kind of immutable by default, but yeah. Conditionally deeply mutable is significantly lower than before. Before we had like 15–16%. Right now we just have about 9%. And I think that it's because in the core library we have this large collections library where certainly we always have generic types and so on. So the immutability always depends on type parameters. And that's less so in Akka actor. Okay, so Scala test, our largest code base that we looked at, right? And again, percentage of mutable declarations is a bit more than 20%, so that's similar to Akka. The deeply immutable ones is a bit lower, 42%. And again, case classes is very similar. Again, like, the percentage is about half, or well, it's much less than half, but there's a big difference here. Here, there's not such a big difference this time. The other point that's also repeated is, again, that singleton objects are just, I mean, here we have 85% or even 97% of singleton objects that are deeply immutable, right? So it's a very simple notion. Right, signal collect, that's a less well-known project. We used it mostly because it only depends on Akka mostly. It's a nice project to analyze. There's lots more mutability in this project. For some reason, even objects are often mutable. That is kind of a code smell, I think. But then again, we again have the situation that, of course, case classes tend to be a lot more immutable. And if you take shallow and deep together, we're at about 2/3. And but here also the numbers are lower compared to other projects. So numbers of templates and so on. Okay, so if you try to summarize the results, then we can say that actually the majority of type definitions in the projects we analyzed already satisfies one of our 3 notions of immutability. right? And deep immutability is often conditional, depends a bit on the project, more so in the Scala core library compared to, let's say, Akka, but we do have to take abstract types into account, right, type parameters. There's a low percentage of mutable case classes, but it's even lower for singleton objects. Yeah. That's quite rare, except for outliers, maybe. I mean, yeah. Right, but we have several, like we have a handful of large projects where the percentage of mutable singleton objects was very low, less than 10%, for example. Right, and so question 2 is, well, if we have a declaration that's not deeply immutable, why is it not deeply immutable? Like, where does the analysis find out, like, get a fact that says it cannot be deeply immutable? And basically, to find out, like, basically we made kind of a list of attributes that declarations can have. So, for example, a declaration could have a mutable parent type. I mean, like, it could have a mutable superclass or a mix in a mutable trait, in which case, of course, the property has to be mutable. And there are other reasons, like it could have a reassignable field. Here we distinguish between public and private, because for private fields we still have the chance that it's not actually stateful. We cannot observe the state, or it's observationally not stateful. We also have, of course, the same for shallow immutable, and we also have this unknown types. And what this basically means is we don't have the source available. Like I mentioned, our handling of external dependencies is not ideal yet. So, for example, if we have a Java type, which happens in the Scala core library, obviously, we sometimes extend a Java class or interface, or we have a val member with Java type, then these are unknown to us. So if you look at only mutable templates in the Scala core library, then there are different reasons for why we had to make it mutable. And in 7% of the cases, it's because the parent type was unknown. So that means, since we're talking about Scala core library, it means that, like, in 7% of cases, the reason is that we extend a Java class or interface. 10% of the cases because we have a reassignable field. But at least in these cases, they're all private. So the public reassignable fields would be in this other, would all be in this orange one, right? Okay, and then 80% actually is that we extend a mutable template, right? And that's, since we have 80%, it means that really, like, a lot of mutability is introduced via inheritance, right? So that's, or mix-in composition. Shallow immutability looks very different. So again, we look at the core library here. And in this case, 33% of the causes for shallow immutability rather than deep immutability, right, is that we have a val field with a mutable type, right, that we know for sure it's mutable according to our or the type does not satisfy one of the notions. And about the same percentage where the parent was already shallow immutable. Again, inheritance is very important here, or mixing composition. And 24%, yeah, have a Java type, essentially, right? So that's for the Scala core library. Of course, that's a kind of a special case compared to other Scala projects, probably. Okay, so if you're interested in more details, you can also have a look at a short paper we wrote about this. Probably extend our results a bit, especially when we can handle dependencies in a better way, you know, so that we reduce the amount of unknown information. But here you can find more details. Also, there's a forthcoming master's thesis by Ludwig Axelsson, and that will have a lot more details as well. And to conclude, well, I think it's really interesting that even with very simple notions of immutability in the most popular Scala projects, the majority of type definitions is immutable, right? Again, case classes and non-case classes are very different, and of course with Dotty we would expect the like enums to be even more different than non-case classes, right? And for singleton objects, there's a very low percentage of them that are actually mutable, and in some projects we had extremely high percentages even for deep immutability, right? And in fact, there are projects like the La Casa project that I mentioned earlier, which would benefit a lot from knowing whether a singleton object is deeply immutable, because that would allow safe access to these kinds of singleton objects. And so I just want to close with a question that we can all discuss over lunch, which is that, you know, is it time for some more support for immutability from the language, where we can reason about immutability using types? All right, so with this, I want to thank you for your attention. Any questions?
When you do your analysis, do you detect mutable usage of mutable objects within the methods of the object, like a print line or something like that? I think you mentioned the different, like you detect if there's vals or if there's vars.
Right.
But within method usage within a class, do you detect global objects that have mutable state and then conclude that that class is mutable? I mean,
right.
there are side effects.
Yeah, so we do not actually analyze side effects in methods. So we really only look at the members and things, right? So that's why it's, what I said is like a rather simple notion of immutability, right? But of course it's interesting to see like what is the effect of methods. Yeah, you don't do that yet.
So is the source code for the analysis available somewhere?
Yeah, sure. You just go to this project on GitHub. Let's see, where is it? Here.
Okay, thank you. Missed that.
Yep. Have you tried to do statistics with runtime value, runtime statistics?
Runtime statistics.
Are they actually use the immutable objects? So what I'm thinking about, you might have some configuration stuff that is mutable. You only use it once, and then you use a lot of immutable stuff in the runtime.
Okay, I see. So you could have the situation where you initialize something. So like you have a mutable object, let's say, that gets initialized in some way, and then at runtime you kind of, once it's initialized, you only access it in a you don't mutate it anymore, basically, right? That's a very interesting question, and we did not analyze that, but there's a very interesting project where people did that for JVM bytecode, as far as I know. So you could probably use that with Scala as well. It's called Spencer, so SPENCER. That was recently released, and that's a project which analyzes the runtime behavior to look at, okay, which things are being mutated at runtime and not, and so on. But we did not do that ourselves. We only looked statically at what we can do with simple static notions. Okay, well, thanks again.